Hi, I'm Archana, an educator and scientist. Today, we will learn about name reactions. Name reactions are very important to convert one functional group in organic chemistry to another. We'll take up today Wittig reaction. Let's begin. I'm sharing my whiteboard. Was the conversion of carbon and functionality to olefins, which is hence it is a very important reaction. So we begin with C6H5, C6H5, C double bond O, which is nothing but benzophenone. And we treat it with triphenyl phosphine alkylidene to obtain C6H5, C double bond CH2. And we are left with C6H5 3. Now, as the name suggests, students, triphenyl means it has three phenyl groups attached to it. So, triphenyl phosphine oxide. So, P double bond O. So, if you want to learn the memory technique in order to write product for any Wittig reaction, I'll tell you right away. So, in this, you can see green color. Or let me make it purple. So, this compound, triphenyl phosphine, as a memory technique, the end product is this triphenyl phosphine oxide. Okay. So this is your memory technique. That is, this will be eliminated. Right. And this is my CH2 group. Right. So C6H5, C6H5, C double bond CH2 will be there. Right. So, or you can write this double bond over here. In that case, double bond from here will be taken and bonded to CH2, ethylene group. So we get triphenyl phosphine oxide. Very simple, right? You need to take the oxygen and attach it to double bond P. And the rest of the group will be attached to your carbonyl compound. So we end up with 1,1-diphenyl. Let us see how we can name it. So the functional group is generally given it as number 1. And this is 2. The functional group is carbon. Anyways, this is only 2 carbons. So 1,1-diphenyl. Substituent group will be given as number 1 and double bond will be given as number 2. So 1,1-diphenyl ethylene. That means you are paying attention. That IUPAC nomenclature is that the carbon with the substituent is given number 1 and double bond is given number 2. So this is your end product of Wittig reaction. Now let us see the mechanism of this particular reaction. So you have mechanism. Right? So you have, let us begin with your carbonyl compound. We know very well that oxygen will always carry a partial negative charge because it's a electronegative atom. As compared to that, carbon will carry a partial positive charge. So this is your carbonyl compound. Now, second compound is R. See, R instead of H, I have put here R. Two alkyl groups are attached to carbon and double bond P, C6H5 twice. Right? Now this bond can open and we can get this kind of compound. This compound carrying positive and negative charge is known as aldehyde. So the carbon containing Let us see the reaction as follows. We have benzophenone that will react with triphenylphosphine alkylidene to give you this compound. Okay, and triphenylphosphine oxide is your byproduct. So let us try to understand how we can write easily end products of this Wittig reaction. What we can do is whatever is depicted in green, that triphenylphosphine oxide, that is the byproduct. This is akka. So you can attach O to this P double bond P and triphenyl group. So your byproduct is there. Rest will be attached to the carbonyl atom. C6H5, C6H5, C double bond CH2. Now if you want to name this alkene compound, then let's see. Now the carbon containing the side chain will be generally given as number 1. So it is given as number 1 and double bond is associated with number 2. So 1,1-diphenyl ethylene is the compound and triphenyl phosphine oxide, as we have already seen, is the byproduct. Now let us proceed for the mechanism. So you have carbonyl compound. We know very well that oxygen carries a partial negative charge, and as compared to that, the carbon will carry partial positive charge. Now, if you speak about phosphorane, now we have already seen that triphenylphosphine alkylidene is also known as phosphorane. So for this phosphorane compound, this double bond can open and it can give a negative charge to carbon, and phosphorus will be having a positive charge. So this compound is known as halide. So the negative portion will go and attack your positive carbon. A lot of students will make a mistake. Phosphorus as compared to carbon, it will be always positive because it has more valency. So it has generally positive charge. Now we will be getting like this kind of compound, right? Where phosphorus will carry a positive charge. This will result into, this is called betaine. Betaine. This will then, betaine structure will rearrange to give you the desired product. Okay, positive negative charge can form bond like this. And in the next step, we will have rearrangement to give this alkene. Triphenyl phosphine oxide. This is rearrangement. Right? Now, what are the application of this compound? Obviously, converting carbonyl group to alkene group or olefin group. Let us take a very simple example of acetone plus CH2 double bond P C6H5. Okay, triphenyl phosphine alkylidene or phosphorane, and you end up with. Now I've told you how to write the end product. Simple, take this O and attach it to this P, and you can easily get the end product. You will end up with a lot of students will make mistake like this. So I showed you how do you make mistakes in a hurry in the exam. You have to see carefully and double bond CH2 plus C6H5 3 times. Double bond. Triphenyl phosphine. Right? This is one method. Now, let us see some more applications of this compound. See some more application of this reaction. So, we took an aliphatic ketone, that is acetone. Let us take, which is this compound, cyclohexanol, right? And I treat it with again phosphorane. So, you have EH3, CH2, right? So this will have positive charge, this will have negative. Simple. What is to be done is, take this, attach it to here, and the rest will be attached to the compound, to the carbonyl, right? So we will be having double bond CH2 plus EH3P double bond, right? This is known as methylene cyclohexane. So you have unsaturation from hexanon, that is ketonic group, you could attach methylene group to the cyclohexane point. Apart from this, you can also utilize it for numerous organic conversion. I'll give you 3 examples to validate this point. So you have triphenyl phosphine, right? And I'll treat it with first isocyanate group. So you have R, N double bond C, N double bond C, double bond O, isocyanate group, right? You can easily introduce double bonding in this isocyanate group and convert it into alkene. So R, N double bond C. Obviously, this portion, as I have mentioned, will go with O, and the rest of the molecule will be like this.